Welcome to another physics lesson. Today we'll be looking at capacitors and capacitance. Our objectives will be to define capacitance and state its formula, to state the factors that affect capacitance, calculate equivalent capacitance, and calculate the energy stored in a capacitor. Now let's look at what a capacitor is. A capacitor is a device used for storing charges or for storing electricity. Don't forget that electricity essentially means the flow of charges. So, devices that are used to store charges or store electricity for use at a later date are capacitors. Capacitors are basically made of two metal plates, which are represented in diagram by the two vertical lines you see on that symbol there. And both plates are of opposite charges and they have a small distance between them. In real capacitors, that distance is not just empty. It has a substance there. It has an insulating material there. And that insulating material placed in between the plates is what is called the dielectric substance of the capacitor. A capacitor is represented by the symbol that you see on your screen. Take note that that symbol has its two vertical lines of equal length. This is different from the symbol of a cell, where you will have the positive terminal of the cell having a longer length than the negative terminal. For a capacitor, both vertical lines have equal length. Please take note of that. What then is the capacitance of a capacitor? This is simply the ratio of the charge on either plate of the capacitor to the potential difference. So in simple terms, we just say that capacitance is the ratio of charge to potential difference. Ratio of charge to the potential difference. Or if you like, you can say charge per unit volts. Charge per unit volts across the plates. That is the definition for capacitance. And from there also, from what we just said, when we say ratio of charge to the potential difference, that just means C equals Q over V. And capacitance, of course, is measured in farads. Even though it has other smaller units like microfarads, millifarads, and maybe even the picofarad, or larger units like the kilofarad, megafarad, but the SI unit is farad. The units you must always perform your calculations with is the farads. Take note of that as well. Now let's look at some factors that affect capacitance. The first of these factors is the distance between the plates. The plates of a capacitor are what is represented by the two vertical lines you saw on the symbol earlier. So the distance between the plates will also affect the capacitance. And it will affect the capacitance by increasing the capacitance if you decrease the distance. Meaning that if you increase the distance, if you make the distance between the plates to be longer, you have essentially decreased the capacitance. So essentially, I'm saying that distance between the plates and the capacitance of a capacitor have an inverse relationship. If one goes up, the other comes down. The second factor is the area of the plates. The plates have a surface area. Even though we represented them by single lines, single vertical lines, you'll find that in a real capacitor, it actually has a metal plate that has an area. It has a length and a breadth. Now, the wider the area, then the more the number of charges that can be stored on them. And if you have more charges stored, that means you essentially have more capacitance. Because remember, C equals Q over V. If your V is constant but you increase the Q, then you have increased the capacitance. So essentially, the area of the plate has a direct relationship with the capacitance of the capacitor. So if the area is increased, capacitance also increases. and vice versa. The third factor is the dielectric constant. Remember we said that in between the plates there is a material called a dielectric substance. So that material is an insulating material. Now the dielectric constant is the ratio of the permittivity of that substance to the permittivity of vacuum. Now every material has the ratio, an extent to which it allows charges to flow through it, has an extent to which it allows things to flow through it. So that is what is called its permittivity. How permeable is it? How easy is it for something to get through? Now the dielectric constant is the ratio of the permittivity of the material you have put in between the plates of your capacitor to that of vacuum. And the higher the dielectric constant of that insulating material, the higher the capacitance of that material. That is the third factor that affects capacitance of a capacitor. Let's then look at a solved example. Here you are given a capacitance of a charge. You are asked to find the capacitance of a charge of 5 times 10 raised to the power minus 8 coulombs. And you also have the potential difference. We already said earlier that C equals Q over V. So you just put the data you are given in the formula and you get your answer. Now, let's now look at the instances where you have more than one capacitor in a circuit. And then you need to be able to calculate the total capacitance in that circuit. In an earlier lesson, we already looked at arrangement of resistors in circuits. We looked at resistors in series and in parallel. You might also want to refer to my YouTube page if you need a review of that lesson. It's there under the topic series and parallel circuits. Now, just as we have for resistors that can be arranged both in series and in parallel, so also capacitors can be arranged either in series or in parallel. So in a circuit where you have more than one capacitors, it's either the capacitors are in series or they are in parallel. At times, you may even have a combination of some capacitors in series and some others in parallel, and all of them are in the same circuit. Now, what do you do to find the total capacitance of the capacitors that have been connected in one way or the other in a circuit? What do you do? What you do is simply by adding them, but in a slightly different way. Let us look at that shortly. When your capacitors are arranged in parallel, again, in the previous lesson, series and parallel circuits, I already explained that parallel arrangements means that you arrange the devices or the components shoulder to shoulder, like they are beside each other, and they are all connected to the same point. Now, in such kind of arrangement, which we call parallel arrangement, the total capacitance is an addition of the individual capacitances. So, if you have capacitors arranged in parallel and you're looking for the total, you just need to add the capacitances of the individual capacitors together. So, for series, however, that is when the capacitors are connected end to end. When you have one capacitor connected to the end of another one, and then they form a long chain. In that case, the total capacitance is the addition of the reciprocal of each of the capacitances. In other words, if you remember very well from our lesson on series and parallel connections, what we are essentially saying is that how you treat resistors in series is how you treat capacitors in parallel, meaning that you just add them up. But how you treat resistors in parallel is how you treat capacitors in series, meaning that you add the reciprocals of the individual values, finding the LCM. Now, after adding the reciprocals, to find the total capacitance, you must also now do the reciprocal of the answer you got. Don't forget that was what we did for resistors in parallel, but now we are doing it for capacitors in series. Looking at your slide now, you can see the two diagrams. The first one is for capacitors in series, the next one is for capacitors in parallel. You can see that in series, the capacitors are arranged end to end. They form one long chain. The charges flowing will get to one first before getting to the next and then getting to the third. But for parallel connections, they are all arranged shoulder to shoulder, like beside each other. Being beside each other means that charges can split up. There is a junction. When we looked at our series and parallel circuits again, we talked about the junction that we have in parallel circuits. So in parallel connections of capacitors also, you have a junction so that some charges can flow down through C1 while others flow continuously and get to the junction of C2. At that junction, some can still flow down to C2 while the others continue to flow to C3. Now, if you now want to add for the ones in parallel, you just add the values of the C's up. Add the values of the capacitances up, like we have in the example that you have on your screen. But if they are in series, you add the reciprocals of their values. Let us see that on the next slide. Let's look at capacitors connected in series then. You have 5 microfarad and 3 microfarad capacitors connected in series. Here is what I mean by saying that you have to add the reciprocals. So 1 over C is 1 over C1 plus 1 over C2. That's 1 over 5 plus 1 over 3. If you find your LCM, you will get your 1 over C to be 8 over 15. But don't forget that we are not looking for 1 over C. We are looking for C, which is a reciprocal of 1 over C. So that means that we must also find the reciprocal of 8 over 15 to get what our C is. And that's 15 over 8. And that's how we are able to get our answer. 1.875 times 10 to the power minus 6 farad, which is equal to 1.875 microfarad. We are then asked to find the charge stored on the plates of the capacitor. From where we started from, we said C equals Q over V. And now we are looking for Q. That means we make it subject of the formula. Q will become CV. And we already found the C on a previous slide. That's 1.875 times 10 to the power minus 6. And the V was also given in the question as 600. So that way we just find our answer. Do not forget that charge is measured in coulombs. Charge is measured in coulombs. And also do not forget, as I said earlier, that we are trying to find a total capacitance. We are trying to use a capacitance value in a calculation. Make sure that the units of that capacitance is in farad. That was why we didn't use the microfarad for this calculation, but we used the farad for this calculation because farad is the SI unit for capacitance. Now, you may also try this. 2 capacitors, 3 microfarad and 2 microfarad are in parallel, which is then connected in series with a 4 microfarad capacitor. That means we have 3 and 2 in parallel. So you must add those ones up first. We now have what you get there in series with 4 microfarad. You now do this the way you treat capacitors in series. Your answer should give you 2.22 microfarad. Please attempt it and see if you can get the correct answer. Now let's look at energy stored in a capacitor. Energy stored in a capacitor. Whenever you have movement of charges, you have electrical energy. So a capacitor stores charges, meaning that it stores electrical energy. Now, while the capacitor is being charged, the charge builds up from an initial value of 0 to a final value of Q. So you are charging a capacitor, the charge is building up. And as it's building up, the potential difference between the plates is also building up from 0 to V. So the average value of the potential difference is 0 plus V over 2. That's how we find average. We add initial and final and divide by 2. That will give us V divided by 2. Now, you'll recall that under our lesson on electrical energy and power, we said E equals QV. But now, our V is not just V anymore. It is rather V over 2. Therefore, the energy stored in a capacitor is QV over 2. That's the first formula for energy stored in a capacitor that you should take note of. The next one, recall also that Q equals CV. We already saw that on this slide. So if Q equals CV, that means that in your formula QV over 2, where you have Q, you can put CV there. So that will give you CV times V over 2. That's CV squared over 2. Also, from Q equals CV, we can see that V will be equal to Q over C. So that means also that in our formula QV over 2, wherever we have V, we can put Q over C there. And that will also give us Q squared over 2C. So we have three formulas that we can use for energy stored in a capacitor. First one is QV over 2. Second one is CV squared over 2. And the third one is Q squared over 2C. Each of these formulas can be used depending on the data you have in the question. And of course, as a physics student, you recall that energy and work done have the same units. They are usually used interchangeably. As a matter of fact, work done is just energy transferred. Now, if we have our energy stored in a capacitor as the formulas that we have looked at, then we can also safely say that the work done in charging a capacitor is given by those same formulas. Work done in charging a capacitor and energy stored in a capacitor therefore are treated the same way. They are both measured in joules. Capacitors, where do they find applications? They are used in ignition systems of motor vehicles. And of course, they are used in radio tuning. When you tune your radio to specific channels, it's because of the capacitor that you have there that you are able to pick your specific channel, at least for the analog radio signals, analog radios that we used earlier. In the days of digital radio signals, they now use more of transistors and diodes. And then lastly, we have the elimination of sparks when a circuit containing inductance is suddenly opened. That is an induction coil. That's a different topic on its own, which we'll be looking at shortly. Let's look at a solved example. A capacitor of capacitance 2 microfarad is connected to a potential difference of 100 volts. Calculate the energy stored in a capacitor. Here, what we have is the capacitance and the potential difference. We have C and we have V. That means the formula that we can use is the one that has C and V in it, and that is E equals CV squared over 2. Now, you have to convert your capacitance to farad. I have said that earlier, that when you're working, you are solving a question on capacitance, the capacitance value must be in farad. And 1 million microfarad makes a farad. That's for those of us who need to know that. 1 million microfarad makes a farad. Therefore, 2 microfarad will be 2 divided by 1 million farad. That's 2 times 10 to the power minus 6 farad. And then our V squared is 100 squared. If we do this right, we get 0.01 joules as the energy stored in the capacitor. Now we are asked to find the charge stored on the plates of the capacitor. Charge is Q. So Q is equal to CV. And the question gave us C. So we have our Q equals CV as 2 times 10 to the power minus 6 times 100. That gives us 0.0002 coulombs. You might try to do your calculations again and see if what we have on the slide is actually right. With that, we have come to the end of this lesson on capacitors and capacitances. We have homeworks to do. Please attempt these questions for your own practice and for further knowledge. And do not forget to drop comments on my YouTube page on whatever it is you need further explanations on, or even if you have a particular lesson you would like me to take you on, please drop a comment on the YouTube page and then we will look at it. I'll be sure to get back to you via that page. Thank you very much for today's lesson. I hope to see you in another lesson sometime soon.